Okay, so this is optimization part 2 and part 3. So we're going to be doing the same thing we did last class, where we are going to get a function, optimize it, which means we maximize or minimize, and then we're going to set it equal to 0, solve for x, and then take that value of x and plug it in where we need to. Okay. But for this one, whoops, well, I guess it's the same for all of them. So for the optimization we've been doing so far, we've had to create the equations and make substitutions. We're going to do the same exact thing here. All right, so example 1, when a management training company prices its seminar on management techniques at $400 per person, 1,000 people will attend the seminar. The company estimates that for each $5 reduction in price, an additional 20 people will attend the seminar. How much should the company charge for the seminar in order to maximize its revenue, and what is the maximum revenue? So our goal here is to create a revenue function and maximize it. Okay, so we're going to create the revenue function from the given information in the paragraph. So we have to set up an equation for price, and we have to set up an equation for the number of customers. So let me just zoom in there, bring this down. So first, let's create an equation for price. All right, actually, we can do this together. We can do price and the number of customers. Okay, so it says, if we have the seminar at $400 per person, 1,000 people will come. So that means if the price is $400, 1,000 people will come. And then if we do a $5 reduction in price, an additional 20 people will attend. So for each $5 reduction, 20 more people come. So that means for price, it's going to be 400 minus 5x, where x is the amount of reductions that we're going to give. And then for customers, every time we do a $5 reduction, a group of 20 people will attend. So you're going to have 1,000 plus 20x. So there is an equation for price and equation for customers. Okay. Now we're going to use those to create the revenue function. Remember, revenue is given by the number of items X times the price P. So here's where we make a substitution like we've been doing for optimization. So for revenue, we're going to get X, the number of items. So this number of customers goes in for X. So we're going to have 1,000 plus 20x times the price. And of course, price goes in for P. 400 minus 5x. Okay, so there's our revenue function. Now we just have to FOIL it out. FOIL it out and simplify. So 1,000 times 400, that's 4, and that's 1, 2, 3, 4, 5 zeros, right? Yep. 1, 2, 3, 4, 5. And then 1,000 times -5, -5,000x. 20 times 400 is 8,000x minus 5x squared. Okay. Now just simplify it and rewrite it with the highest power first, and we'll get -5x squared. You can put the x's together. -5,000 plus 8,000 gives me 3,000 plus 400,000. Here is our revenue function. And now our job after finding the revenue function is to maximize it, which means we're going to take the derivative, set it equal to 0, and solve for x. Any questions so far?
Okay, so what we did is that we foiled and then we combined like terms.
Exactly.
That's it.
That's it.
Okay.
That's it. Now we do calculus. So now we're going to take the derivative of the revenue function, which is above, which is negative 10x plus 3,000. Oh, did I miss the number? What did I do? Oh, I messed up. What's 20 times 5?
100. I was looking at that. I was going to ask you at the end.
100x squared. I was like, oh man. Oh, good. Glad we caught it now. There we go. Negative 100x squared plus 3,000x plus 400,000. Okay. I started doing the derivative. I was like, this doesn't look right at all. All right. Now we do the derivative and we get negative 200x plus 3,000. You set the derivative equal to 0. So negative 200x plus 3,000 equal to 0. And then move that 3,000 over. Sure. And then divide by negative 200. All right. So this means we're going to get x equals, and we know that negative over negative makes positive. And look at this fun trick. Cancel those zeros, and 30 over 2 is 15. So 15 is the number of price reductions we're going to give to get groups, 15 more groups of 20 people in. So this will be reductions. Okay, and now all we're going to do is take this number 15, plug it into the revenue function, and plug it into the price and customer equation. So plugging 15 in will give us the maximum revenue. It'll give us the price we're selling the tickets at, and it'll give us the amount of customers that come in. So we're going to plug it into all three of those. Let's knock out the hard one first. We'll do revenue. So R of 15 gives me negative 100 times 15 squared plus 3,000 times 15 plus 400,000. Calculate that, and our maximum revenue is going to be $422,500. This is max revenue. Okay. Now just plug it into the price equation. Let me change this. All right, this pen's getting annoying. Ugh. Let's see. This is not the pen, and it's the laptop. We shall see. Definitely was the pen. Okay. And price was 400 minus 5x. So you have 400 minus 5 times 15. So that's going to give us 325 per ticket or per person. And then last would be number of customers. And that is 1,000 plus 20x. So 1,000 plus 20 times 15. And we are going to get 1,300 customers. Okay. So if we do 15 price reductions and sell the tickets for $325 per person, 1,300 more customers will come and we'll make $422,000 at this seminar. It's like those seminars on how to make you rich, right? Look at that. Look at that revenue, man. So you paid $300 just to learn how to get rich.
Get rich quick.
There you go. And all they tell you in that seminar is do what we're doing. You make a seminar and you charge people and tell them how to make money.
Yeah. No, I've been to one that it was free, but then at the end they're like, "Oh, if you come sign up right now, we're gonna knock off this much money. So come and do it now," and this and that.
Nope, nope, nope.
So
nope.
they're trying to hook you on the first one. That's a freebie, and then the next ones are like, "All right, come on."
That's how you get rich.
Better than pyramid schemes, though.
Yeah, I
Yeah.
guess so. It's about this, almost the same. All right. Any question on that problem? That's how you're going to set these guys up in your homework. You're going to create a revenue function. And these types of problems, you are always going to treat as a revenue function. So the problem may say, what is the income? What is the gross profit? You are always going to create a revenue function. And the reason being is because in the problem, it's always giving you an amount of items, like here, the number of customers, and it's always giving you a price. So remember that revenue is always items times price. Okay, let's try another one. Car rental. A car rental agency rents 200 cars per day at a rate of $30 per day. For each $1 increase in rate, 5 fewer cars are rented. At what rate should the cars be rented to produce the maximum income? And what is the maximum income? So here we are going to maximize income, but remember, this is the same as a revenue equation. So let's first start off with, I guess we could call this step A. Let me zoom. There we go. And in step A, let's go ahead and create a price equation and a number of cars equation. So A, we're going to say price and cars. Okay, so for price, how much are we renting these cars for per day?
$30 per day.
$30. And if we rent them at $30, how many cars do we have?
200.
200. And then we say, hey, let's go ahead and increase the rate by $1. So that's going to be 30 plus 1x. So that 1x represents each $1 increase. But if we increase the rate by $1, how many cars are we going to lose?
5.
5. 5 per increase. There we go. And there's our price equation and our cars equation. Now let's make an income / revenue equation. So B, revenue. R of X equals, and it's going to be the number of items, so cars, 200 minus 5x times the price, 30 plus x. Now here we will FOIL, and let's do it right this time, right? 200 times 30, that's 6, and that's 3 zeros, 1, 2, 3. And then that's 200x minus 150x. And hey, there's a negative 5x squared this time. Perfect. Okay, clean it up, combine like terms, write it with the highest power first. And you can put these two together, which will give me 50x plus 6,000. And there's our revenue equation. Or income, sorry. Income slash revenue. I'll put that there. All right. Now, since we have the revenue equation, we are going to optimize it. We're going to maximize it. So this means we're going to find the derivative. So I'll just say maximize R of X. So that means we find the derivative, R prime of X, and that's going to be negative 10x plus 50. And after you do that, you set it equal to 0 and solve for X. Divide by negative 10, and you should get X equals 5. That is the number of rate increases. Okay, so we're only going to do 5 rate increases, so rate of $5. So now, again, what we're going to do with that information is plug it into the revenue function, plug it into the price, and plug it into the cars. So I'll have R of 15, not 15, 5. And I'll have negative 5 times 5 squared plus 50 times 5 plus 6,000. And our maximum income or revenue is going to be $6,125. Okay, and now just plug it into price and cars. $30 plus 5. We're going to charge $35 per day. And if we raise our rate by $5, then we are going to lose out on people renting our cars. And cars was 200 minus 5x. So 200 minus 5 times 5. And if we do a $5 increase, we're only going to rent out 175 cars that day. Okay, and there it is. Any questions on that setup? Okay. So again, for these type of problems, treat them as revenue. You're going to create the price. You're going to create the number of items equation, and then you'll make a revenue function, and then you'll maximize it or minimize it, whatever it wants you to do, which means all that means is take the derivative, set it equal to 0, solve for X, and then plug it into revenue, plug it into the price, plug it into the number of items.
Question.
Yes.
Even when it says, like, if it were to say minimize the income, I don't know if it's ever going to ask me that, but is that the same thing as finding the derivative?
That's it. So it doesn't matter if you maximize or minimize, it's the same exact process.
Okay, sounds good.
The only difference would be the way the problem asked it. That's it. Okay, cool. So example 3 is just like the other two. We can work it or we can save time by skipping it. What do you want to do?
Skip it, skip it.
Are we good skipping?
Yeah.
Okay, okay.
Yes.
All right, which means that finishes part 2, which brings us to part 3. Inventory control. All right, so here we want to optimize. So we want to maximize or minimize the cost of creating inventory. So for inventory control, X is the number of items, Y is the number of production runs to create X amount of items, and X over 2 is the average number of storage each day. So they came up with this X over 2 equation. Let's say you have a warehouse. One day it's full, the next day is empty, the next day it's full, one day it's half, and then it keeps going on like that for a year. So X over 2 represents the storage, the average number of storage each day. Okay. So in these problems, we're going to have to create a storage cost and a setup cost equation. So storage cost is always the cost to store an item times X over 2. Setup cost is the cost to set up times Y, the number of production runs. And once we have storage cost and setup cost, we will create a cost function, which is made up of the storage cost and setup cost equation. So once again, we are creating equations, we're creating formulas, and then we're substituting them in, just like we've been doing for optimization. And then one more equation that we have to deal with is the annual demand of items, which is going to be X times Y. It's how much people demand to be made, or whatever we demand to be made to be sent out to the stores. Okay, so maybe it looks like a bunch of information, but it's not too bad. And the paragraphs, the problems, always give you the information you need. So let's try number 1 out. A multimedia company anticipates that there will be a demand for 20,000 copies of a certain Blu-ray during the next year. It costs the company 50 cents to store a Blu-ray for 1 year. Each time it must make additional Blu-rays, it costs $200 to set up the equipment. How many Blu-rays should the company make during each production run to minimize its total storage and setup cost? Okay, so first thing we're going to do is create the storage cost and setup cost equations from the given information in the paragraph. All right, first up, we'll do storage. And in the paragraph, how much does it cost to store a Blu-ray?
50 cents.
50 cents. And for storage cost, we take that 50 cents and multiply it by X over 2. And half of 50 cents is going to be 25 cents X. There's the storage cost. All right, next is the setup cost. Every time we want to make new Blu-rays, how much does it cost to set up the equipment?
200.
200. And we use that setup cost up there, which means you just multiply 200 by Y, which gives us 200Y. Okay. And now we're going to create the cost function, which is made up of storage cost plus setup cost. So my cost function is 25x plus 200y. Okay, there's that. And now what we want to do is minimize the total storage and setup costs. We want to minimize the cost function, but we can't take the derivative of the cost function until we get rid of that pesky y again. So we have to make a substitution. And the only way to do that is by using the demand equation. So looking at the paragraph, how many Blu-rays are demanded?
20,000.
20,000. So here's what we're gonna do in step C. How much can I zoom in? That's perfect. So the demand equation is xy equals 20,000. Now we're gonna solve this equation for y, which means we're gonna divide by x. And y is equal to, there we go, is equal to 20,000 over x. This is now my sub. That's what we've been doing. And you're going to plug that in for the y into the cost function. So that means we're going to have c of x is equal to 0.25x plus 200 times my substitution for y, which is, oops, 20,000 over x. Now we just simplify this and we get 0.25x plus 200 times 20,000. That's 4. And how many zeros do I have? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And I'm going to take this x and flip it to the numerator. So it's going to be 4 million x to the negative 1. And here's my new cost function, all in terms of x. We got rid of that pesky variable y. Okay. Which means we can move on to the next step. We're going to minimize the cost function, which means take the derivative, set it equal to 0, and solve for x. Zoom, zoom, there we go. All right. I think that's perfect. So we'll take that derivative. C prime of x is going to be 0.25 minus 4 million x to the negative 2. Now set your derivative equal to 0, and you get 0.25, just 0.25 minus 4 million x to the negative 2 equal to 0. Add that 4 million to the right side, and you get 0.25 equal to 4 million. And what I'm going to do again is take this x to the negative 2 and flip it back to the denominator. And since we're solving for x, we need to get it out of the denominator. So we're just going to multiply it to the left side. So we get 0.25 x squared equal to 4 million. Now divide by 0.25. And 4 million divided by 0.25 is basically 4 million divided by a fourth. So you would multiply by the reciprocal or just type it in your calculator. And this should give me 16 million. Okay. And now square root both sides. And we will get x equals plus or minus, and that is that 4,000? Let me see. Yes, you get x equals 4,000. Now, since we're talking about items and we're in the business world, can we have negative 4,000 Blu-rays?
No.
No. So we only take the positive one. So this would just be 4,000 Blu-rays. Okay. So now all we have to do is take this value of x and plug it into the y substitution to solve for y, and then plug it into the cost function for x. This will give us the minimum cost, and it will give us the number of production runs. All right, so let's do this. Let's see. So y equals 20,000 over x, or 20,000 over 4,000, which gives me 5. And remember, in these types of problem, y is the number of production runs. So this is production runs. So this means that every production run, we're going to make 4,000 Blu-rays until we get to 20,000 Blu-rays. So 5 times 4,000, 20,000. Okay. And then last, plug it into the cost function. And I'll do purple. You have C of 4,000 equal to 0.25 times 4,000 plus 4 million times 4,000 to the negative 1. And what is our minimum cost going to be? Let's see. That's going to be $2,000. That's the minimum cost. Okay. So I'm pretty sure that's the minimum cost per production run. But it said, how many Blu-rays should the company make during each production run? So we should make 4,000 Blu-rays each time during 5 production runs, and we will minimize the storage and setup costs to $2,000 each time. Okay, any questions on that?
So what difference is there between this part 3 and the part 2? It looks almost identical.
Part 2, we had to make a revenue function. Part 3, we're making a cost function from setup and storage.
Okay, sounds good.
Yeah. Okay. All right, one more just like this, and we're done. All right. Example 2. A tool company has a uniform annual demand for 9,000 premium chainsaws. It costs $5 to store a chainsaw and $2,500 to set up the plant for manufacture of the premium model. How many chainsaws should be manufactured in each production run in order to minimize the total storage and setup costs? So we're going to do the same exact thing. So we'll call this step A. Let's get our setup and storage cost. So storage and then setup. So for storage, it says it costs $5 to store a chainsaw. So 5 times X over 2, 2.5X. Setup, it says it costs $2,500 to set up each time, and it's 2,500 times Y. So 2,500Y. There's that. Okay. B, make the cost function. So that means that C of X is going to be storage costs plus setup cost. And there's the cost function. And now we have to make a substitution using the demand equation. And it says that 9,000 chainsaws are demanded. So C, for demand, we have XY equals 9,000. Solve this for Y, and you'll get Y equals 9,000 over X. Again, here's our sub that goes in for that Y value. So let's call that step D. So we'll have C of X equal to 2.5X plus 2,500 times my new Y value. And I'm just going to write it like this already. 9,000 X to the negative 1. Just take that X from the denominator and flip it up. Okay, clean up. 2.5X plus 9 times 25,000. 9 quarters, $2. Yes. So you're going to get 22,500,000 X to the negative 1. There's our new cost function, all in terms of X. Okay. Which means since we have the cost function, we can now optimize it, which means we're going to take the derivative, set it equal to 0, and solve for X. So I'll just say optimize. And go blue. C prime of X gives me 2.5 minus 22,500,000 X to the negative 2. Set it equal to 0. move the 22 million over. And flip that x squared underneath. And multiply it to the left side. Here you'll get 2.5x squared equal to 22,500,000. Divide by 2.5. And if I divide by 2.5, that should give me 9 million. Where all we have to do next is square root both sides. And we're only going to take the positive value, and the square root of 9 million is 3,000. And that's going to be the number of chainsaws. Woohoo! And of course, all we have to do now is take 3,000, find y. So plug it in for the y substitution and plug it in for the cost function. And we'll be done. So let's try that. F. So we'll have y equals 9,000 over 3,000, which means we'll do 3 production runs per year. And then we'll do C of 3,000, and you'll get 2.5 times 3,000 plus 22,500,000 times 3,000 to the -1. And the minimum cost for producing, what is it? Oh, for an annual demand of 9,000 chainsaws, we're going to be spending $15,000 each production run. So this will be $15,000. There's our minimum cost. Bam. And there it is. That is optimization, guys. Any questions on this last one?
No.
Wow.
Good. Once you have the setup down, everything else should be smooth, hopefully, from there, right? Okay, well, that means we're done. There's time left if you have questions over the homework or the test review. Other than that, your test will be Tuesday. And yeah, I won't see you till next Thursday.
Okay, thank you. Have a good night.